Mars is trying to kill you, not metaphorically, not as a distant theoretical risk. Right now, at this very moment, the surface of Mars is bathed in radiation that would deliver a lethal dose to an unprotected human body within days. The atmosphere is 95% carbon dioxide, so thin it offers almost no protection, so toxic it would suffocate you in seconds. The temperature swings 200 degrees Fahrenheit between day and night. Dust storms the size of continents can last for months. And yet, we are going anyway. The question isn't whether we'll attempt it. The question is whether we'll survive it. For most of human history, Mars was a mystery written in firelight. Ancient astronomers watched it drift across the night sky, reddish, wandering, unlike the fixed stars, and they named it after gods of war. The Babylonians called it Nergal, deity of death and plague. The Romans saw blood in its colour. Even before we understood what it was, something about Mars unsettled us at a primal level, as though the universe itself was issuing a warning. Fast forward to the 20th century, we send probes, we get our first close-up photographs, and the warning becomes a measured scientific reality. The Mariner 4 spacecraft made its historic flyby in July of 1965, transmitting 22 grainy black and white images back to Earth. Scientists crowded around early printouts, literally colouring them by hand with pastel crayons, too impatient to wait for the computer rendering. What they saw shattered a century of hopeful speculation. No canals, no vegetation, no signs of civilization, just craters, just rock, just an ancient, battered, airless-looking world that appeared by every measure profoundly dead. That was our first real look at Mars, and the scientific consensus that emerged from the following decades of missions was sobering. Mars is not just uninhabited. Mars is, in almost every meaningful sense, hostile to life as we know it. But here's where it gets interesting. Because even as robotic explorers confirmed Mars's brutality, they simultaneously revealed something astonishing. Something that rewrote our understanding of what Mars once was and what it might one day be again. Mars wasn't always like this. Billions of years ago, Mars had a thick atmosphere. It had a magnetic field. It had liquid water. Not just traces, not just ancient ice, but oceans. Real, standing, flowing water. Lakes and rivers and perhaps entire seas. Mars was, once upon a time, a world that might have harboured life. What happened to it? That question has become one of the most important in modern planetary science, because the answer tells us not just about Mars, it tells us about Earth. It tells us how fragile the conditions for life truly are. It tells us what a planet looks like when those conditions collapse, and it tells us, with cold precision, exactly what challenges await any human being who sets foot on Martian soil. To understand whether we can survive Mars, we first need to understand what Mars is doing to survive without us. The planet's diameter is roughly half that of Earth, about 6,779 kilometers, compared to our 12,742. Smaller, yes, but not small. Mars is larger than Mercury, large enough to hold the tallest volcano in the entire solar system, Olympus Mons, a shield volcano so massive it covers an area the size of France and rises nearly 22 kilometers above the surrounding plains. For comparison, Mount Everest reaches just 8.8 kilometers above sea level. Olympus Mons is almost 3 Everests stacked end to end, and it sits on a planet with barely 1% of Earth's atmospheric pressure. That number, 1%, is perhaps the single most important figure in the entire discussion of Mars colonization. It is not a minor inconvenience, it is a fundamental barrier to human survival. At 1% atmospheric pressure, the boiling point of water drops so dramatically that liquid water cannot exist on the open Martian surface. Expose a glass of water to Martian atmospheric pressure, and it will simultaneously boil and freeze, a phenomenon called the triple point, where all 3 states of matter exist momentarily before the water simply sublimes into vapor and vanishes. Your blood would do something similar if you stepped outside without a pressurized suit. The moisture in your lungs would boil. You wouldn't suffocate first, you would effectively explode from the inside. Then there's the cold. The average surface temperature on Mars is around -60 degrees Celsius, -80 degrees Fahrenheit. At the poles in winter, temperatures plunge to negative 125 degrees Celsius. Even at the equator, on a summer afternoon, temperatures might briefly climb to around 20 degrees Celsius, almost pleasant, almost Earth-like, before plummeting below -70 when the sun goes down. That 200-degree daily swing isn't just uncomfortable. It stresses materials to the breaking point. Metal contracts and expands, seals fail, habitats crack. Any structure on Mars must be engineered to survive thermal cycling that would destroy most conventional construction on Earth. What does the radiation situation look like? On Earth, we are protected by two invisible shields working in concert. First, our magnetosphere, the planet's magnetic field, generated by its molten iron core, deflects most of the charged particles streaming from the Sun. Second, our thick atmosphere absorbs much of what gets through. Mars lost its magnetosphere approximately 4 billion years ago, when its core cooled and solidified. The atmosphere slowly bled away into space without that magnetic protection. And now Mars sits exposed, unshielded, absorbing the full punishment of solar radiation and galactic cosmic rays. NASA's Curiosity rover has been measuring radiation on the Martian surface since 2012. Its instruments recorded an average radiation dose of about 0.67 millisieverts per day, roughly equivalent to 35 chest X-rays every single day. Over a 500-day surface mission, an astronaut would accumulate radiation exposure exceeding the lifetime limit set by NASA for its crew members, and that's just the background baseline. A major solar energetic particle event, a solar flare or coronal mass ejection, could spike that exposure to lethal levels in a matter of hours, and then there is the dust. Martian dust is not like the dust on your bookshelf. It is fine, extraordinarily fine, with particles small enough to penetrate most filter systems. It is pervasive. It coats solar panels, reducing power generation. It infiltrates mechanical joints. It has been found to contain perchlorates, chemical compounds that are toxic to the human thyroid gland and can disrupt metabolic function. Breathe enough of it, and you face chemical poisoning layered on top of everything else. This is the environment awaiting the first human visitors to Mars. The question we must ask, the question that aerospace engineers, medical researchers, planetary scientists and psychologists are grappling with right now, in labs and simulations and research stations across the planet, is deceptively simple. Given all of this, given every single one of these lethal variables, can a human being not just visit Mars but actually live there? The answer, it turns out, is far more complicated than yes or no. Because the remarkable thing, the thing that gives the most serious researchers genuine hope, is that every single one of these problems has a potential solution. The radiation can be shielded. The atmosphere can, in theory, be thickened. The cold can be managed. The dust can be filtered. Water can be extracted from ice buried beneath the surface. Food can be grown underground. Energy can be generated. None of it is easy. None of it is certain, but none of it is impossible. And that distinction between difficult and impossible is where the entire story of Mars colonization lives. But that's not the full story. Because even if we solve the physical problems of Mars, a new and perhaps more unsettling challenge awaits. One that doesn't show up in atmospheric pressure readings or radiation dosimetry charts. One that lives inside the human mind itself. Let's establish the current state of ambition. In 2024, NASA's Artemis program was actively laying groundwork for eventual Mars missions, with agency leadership publicly targeting crewed Mars landings in the late 2030s or early 2040s. SpaceX's Starship, the most powerful launch vehicle ever constructed, standing nearly 123 meters tall and capable of lifting over 150 metric tons to low Earth orbit, was designed from the outset with Mars as its primary destination. Elon Musk has spoken about establishing a self-sustaining city on Mars of 1 million people within the next few decades. The European Space Agency, China's CNSA, and private ventures from multiple countries are all investing in Mars exploration infrastructure. This is not science fiction. This is active, funded, engineering-driven ambition. But ambition without preparation is just fantasy, and the preparations required for a crewed Mars mission are unlike anything humanity has ever attempted. Consider the journey alone. At its closest approach, a configuration called opposition, Mars is approximately 54.6 million kilometers from Earth. That sounds like a lot, and it is. But Mars doesn't stay at closest approach. Its orbit is elliptical, and the geometry of the two planets' paths around the Sun means that the optimal launch windows, the periods when the journey requires the least fuel and the shortest travel time, occur roughly every 26 months. Miss one of these windows and you wait more than 2 years for the next. During an optimal transfer using current chemical propulsion technology, the journey takes approximately 7 to 9 months. That's 7 to 9 months in microgravity, in a spacecraft with limited radiation shielding, in a confined environment with a small crew, before you even arrive. And then, because of those orbital mechanics, you can't simply turn around and come home when you want. You must wait on Mars, anywhere from 30 days in some mission architectures to 500 days in others, for the planets to realign before the return window opens. Total mission duration, somewhere between 2 and 3 years, 2 to 3 years away from Earth, away from sunlight you can step into without a suit, away from fresh food, away from the gravitational force your body evolved under, away from immediate medical help if something goes catastrophically wrong. What does microgravity do to the human body over that time frame? We have substantial data from the International Space Station, where astronauts regularly spend 6-month rotations, and occasionally longer. The findings are instructive and in some cases alarming. Bone density decreases at approximately 1 to 2% per month in the lower limbs, even with rigorous daily exercise regimens. Muscle mass degrades. Fluid shifts upward in the body, creating constant head pressure and altering vision. A condition called spaceflight-associated neuroocular syndrome, which has been found to structurally change the shape of astronauts' eyeballs and potentially cause permanent visual impairment. The cardiovascular system weakens because the heart no longer needs to work against gravity to push blood upward. The immune system shows disruptions. Sleep architecture changes. After 6 months in microgravity, returning astronauts often cannot walk unassisted. They must be carried from their Soyuz capsules. It takes months of rehabilitation to restore normal physical function. Now imagine arriving at Mars after 9 months in those conditions, and then being immediately required to perform high-stakes, physically demanding work on a planet with 38% of Earth's gravity. Not the zero gravity of the transit, 38%. Enough to walk, but enough to feel different in every movement, every breath, every heartbeat. Enough to demand physical capability from a body that has just spent 9 months deteriorating. NASA's Human Research Program has identified 5 primary hazards of spaceflight for long-duration missions: space radiation, isolation and confinement, distance from Earth, gravity fields, both the absence during transit and the altered field at destination, and hostile and closed environments. They call these the 5 hazards. Mars missions face all 5 simultaneously, for longer than any previous human spaceflight endeavour, at a distance where communication delays alone could mean life or death. The speed of light is approximately 300,000 kilometers per second. At average Mars-Earth distances, that means a one-way communication signal takes between 3 and 22 minutes. In an emergency, a crew calling Earth for guidance faces an agonizing wait of 6 to 44 minutes for a round-trip exchange. There is no real-time help. There is no mission control that can intervene in the moment. Every decision, every emergency response, every judgment call, it all falls on the crew, and the crew will be small. Current mission architectures typically envision 4 to 6 people, 4 to 6 human beings, alone in the universe, separated from the rest of humanity by distances that make even radio communication an exercise in patience, dependent entirely on their own knowledge, their own equipment, their own psychological resilience. What happens to the human mind under those conditions? Research from Antarctic overwinter stations, isolated, confined environments that offer the closest Earth-based analogue to a Mars mission, provides a window into what crews face. These scientists have observed a phenomenon called third-quarter syndrome, where morale, motivation, and psychological cohesion tend to sharply decline approximately 3/4 of the way through an isolated mission. Interpersonal conflict intensifies, cognitive performance degrades, depression and anxiety rates climb. Some individuals experience a kind of emotional withdrawal, a psychological shutting down that researchers describe as hibernation behavior. In Antarctica, If things get bad enough, you can be evacuated. It's difficult and dangerous in winter, but it's possible. On Mars, there is no evacuation. And yet, here is where the story shifts. There is also no shortage of people willing to go. When Mars One, a now-defunct private initiative, announced in 2013 that it was accepting applications for a one-way Mars colonization mission, over 200,000 people applied. Understanding why so many humans are drawn towards something so obviously dangerous tells us something profound about our species. It tells us something about why we have survived every hostile environment Earth has thrown at us, from the Arctic to the deep ocean floor. It tells us that survival is not just a physical calculation, it is a motivational one. But what happened next in Mars mission research would shock even the most optimistic researchers. Because as they dug deeper into the problem of surviving Mars, they didn't just find dangers. They found, buried in the data, some genuinely extraordinary possibilities. Solutions so elegant, and so surprisingly within reach, that the picture of Mars survival began to look less like a death sentence and more like, in the words of planetary scientist Dr. Robert Zubrin, the greatest adventure in human history. Now here's where it gets truly strange. For decades, the fundamental assumption about Mars colonization was that we would need to bring everything with us. Every breath of air, every drop of water, every gram of food, every kilogram of construction material. The sheer logistics of that vision made Mars colonization seem almost impossibly expensive, a sustained effort that would require launching millions of tons of supplies from Earth every 2 years, forever. That assumption was wrong. Mars, it turns out, is not an empty wasteland. It is a resource-rich world. And the realization of just how many of Mars's resources could potentially be harvested, processed, and used by human settlers has transformed the entire economics and feasibility of Martian survival. Start with water, the most critical resource for any human presence. In 2018, the European Space Agency's Mars Express orbiter, using its MARSIS radar instrument, detected what appeared to be a subglacial lake of liquid water beneath the southern polar ice cap, located approximately 1.5 kilometers below the surface, roughly 20 kilometers in diameter. It was the first direct evidence of a stable liquid water body on present-day Mars. The detection was later confirmed and expanded upon by subsequent radar surveys, with additional potential subglacial features identified nearby. But the deep polar subsurface isn't the only place water hides on Mars. Water ice exists in vast quantities in the polar caps, both visible surface ice and layers buried beneath dust and rock. More remarkably, radar surveys have detected shallow ice deposits at mid-latitudes, regions of Mars where solar energy is more accessible, where temperatures aren't quite as extreme, and where colonists might actually want to live and work. In some locations, pure water ice exists within just centimeters of the surface. Some models estimate that the volume of water ice on and just beneath the Martian surface could, if melted, form a global ocean up to 35 meters deep covering the entire planet. 35 meters of water, globally distributed, already there. For a Mars colony, this changes everything. Water doesn't just sustain human life directly, it is the feedstock for rocket propellant. Split water molecules through electrolysis, and you get hydrogen and oxygen. Combine hydrogen with the carbon dioxide in the Martian atmosphere, and you can synthesize methane, exactly the propellant used by SpaceX's Raptor engines which power Starship. A Mars colony capable of producing its own propellant doesn't need to import rocket fuel from Earth. It can manufacture the means of its own return, and eventually the means of expansion. This concept, using local Martian resources to sustain and fuel a colony, is called in situ resource utilization, or ISRU. It is not theoretical. NASA's Perseverance rover, which landed in Jezero crater on February 18, 2021, carries an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE is a small device about the size of a car battery. Its purpose is to produce oxygen directly from the Martian atmosphere by running CO2 through a solid oxide electrolyzer. Between 2021 and 2023, MOXIE produced oxygen on Mars multiple times. In its most successful run, it generated 10.44 grams of oxygen in 1 hour, enough to sustain a human for approximately 20 minutes of normal breathing. A full-scale version of MOXIE, roughly 200 times larger, could theoretically produce enough oxygen to sustain a crew of 4 and provide oxidizer for rocket propellant. So, water from ice, oxygen from air, fuel from local chemistry. What about food? Growing food on Mars faces severe challenges, but not insurmountable ones. The Martian soil, called regolith, is chemically problematic. It contains those perchlorates we mentioned, toxic compounds that would need to be chemically removed before food could be grown in raw Martian soil. But regolith also contains essential mineral nutrients: iron, magnesium, calcium, sodium. With perchlorate removal and the addition of nitrogen, which can be extracted from the trace amounts in the Martian atmosphere, Martian regolith can potentially be transformed into a workable growing medium. Research into controlled environment agriculture has advanced dramatically in recent years, driven partly by the demands of long-duration spaceflight. Hydroponic and aeroponic systems, growing plants in nutrient-rich water or misted air without soil, have achieved extraordinary efficiency gains. More LED grow lights tuned to specific wavelengths for photosynthetic optimization have reduced energy requirements. Crops like potatoes, sweet potatoes, radishes, and certain leafy greens have been tested under simulated Martian conditions and shown genuine viability. In 2021, researchers at Wageningen University in the Netherlands successfully grew 10 different crop species in simulated Martian regolith, including tomatoes, radishes, rye, and garden cress, with yields comparable to Earth-grown controls after perchlorate removal. A crew could, in principle, supplement their supply-shipped rations with locally grown food. Over time, a colony might become genuinely food independent. Underground habitats solve multiple problems simultaneously. Buried beneath a few meters of Martian regolith, a habitat is shielded from the majority of surface radiation. The regolith itself acts as insulation, moderating temperature extremes. Underground structures are protected from dust storms, and lava tubes, the remnant tunnels left behind by ancient Martian volcanic activity, have been identified as potential ready-made shelter locations. Some of these tubes may be kilometers wide, potentially large enough to enclose entire communities under a pressurized dome. This means that the picture of a Mars colony isn't necessarily one of fragile surface habitats trembling under radiation and dust. It might be a thriving underground civilization, tunneling deeper over generations, expanding into a network of pressurized spaces carved from the Martian rock itself. Consider what that civilization might look like over decades. First, would a small crews of explorers, 6 to 12 people in pressurized modules, conducting science, testing ESRU systems, expanding their footprint year by year. Then, as the infrastructure matures, larger crews, permanent residents with no immediate return date. Children, eventually and born on Mars, adapted from birth to 38% gravity, to the rhythms of a 24-hour and 37-minute day, to an existence where going outside means suiting up without exception. What would those children be? Martians? Humans? Something between? But we are getting ahead of ourselves, because before any of that is possible, before any colony can be established, the immediate crisis of the transit journey must be solved, and the solutions being developed for that journey are, in themselves, remarkable enough to deserve our full attention. Over the implications of this discovery, that Mars is far more resource-rich than we imagined, are almost too vast to comprehend. Because it means the question has shifted. It is no longer, can we survive on Mars? It is, how fast can we build the infrastructure to make survival possible? Those are profoundly different questions, and the second one has answers. Here is the moment where everything converges. We have established what Mars is trying to do to the human body. We have established that the resources to survive are actually there, waiting beneath the surface and locked in the chemistry of the atmosphere. Now we must ask the hardest question of all, the one that lives in the space between ambition and reality. What does an actual working human survival system on Mars look like? Not in general terms, in specific ones. The journey begins before the crew ever boards the spacecraft. Years before launch, in what mission planners call the pre-deployment phase, cargo missions carry supplies to Mars ahead of the crew. Fuel production systems begin operating autonomously, building up propellant reserves for the return trip before a single human being has left Earth. Habitats are delivered and inflated or assembled by robotic systems. Life support systems are tested and run through thousands of hours of operation. Power systems, likely a combination of solar arrays and small nuclear fission reactors, are switched on and begin charging batteries, running heaters, maintaining pressure in empty habitats that await their occupants. By the time the crew launches, they are not arriving at a blank wilderness. They are arriving at a base. And this is the architecture championed most vigorously by Dr. Robert Zubrin, aerospace engineer and founder of the Mars Society, in his Mars Direct plan. First proposed in 1990 and still influential in virtually every serious Mars colonization architecture developed since. The core insight is simple but powerful. Don't try to make Mars livable by launching from Earth everything you need. Send the tools to make Mars livable using what Mars already has. The spacecraft itself represents the first survival challenge. SpaceX's Starship, in its interplanetary configuration, is designed to carry up to 100 people on the Mars journey. Though early crewed missions will likely fly far fewer, perhaps 4 to 12, to reduce risk and optimize crew selection. The transit habitat must provide everything the crew needs for 7 to 9 months: food storage, water recycling, air recycling, exercise equipment, medical facilities, psychological support systems, communication systems, and radiation sheltering. The radiation sheltering component during transit is where current engineering faces its most significant challenge. The transit habitat can be partially shielded using water tanks positioned around sleeping and high-activity areas. Water is an effective absorber of certain types of radiation. Polyethylene, a hydrogen-rich plastic, is also effective, but shielding sufficient to reduce radiation exposure to acceptable long-term levels adds enormous mass, and mass is the fundamental currency of spaceflight, always expensive, always limiting. One emerging solution is pharmacological. Research teams at NASA and partner institutions are investigating radiation countermeasures, drugs that can either protect against radiation damage in real time or accelerate cellular repair after exposure. A compound called amifostine has shown some radioprotective properties in clinical settings. More promisingly, researchers are exploring the potential of drugs that modulate the body's DNA repair mechanisms, compounds that essentially tune up the cellular machinery that fixes radiation-induced genetic damage. In 2023, a research team at the University of California, San Francisco identified a drug compound that dramatically reduced radiation-induced cognitive decline in mouse models. Exactly the kind of cognitive damage that long-duration space radiation is expected to cause in human crews. We are not yet at human trials for Mars-specific radiation protection, but the trajectory is clear. Another solution is time. Faster transit reduces exposure. NASA and various research institutions have been investigating advanced propulsion concepts that could cut transit time from 9 months to as few as 3 or 4 months, dramatically reducing cumulative radiation dose. Nuclear thermal propulsion, which heats propellant using a nuclear reactor rather than chemical combustion, could theoretically achieve specific impulse 2 to 3 times better than the best chemical rockets. NASA's Draco program, a collaboration with DARPA, was actively developing a nuclear thermal propulsion demonstration mission as of 2024. A flight test is planned for the late 2020s. Laser thermal propulsion, ion drives, even more exotic concepts like solar sails. The physics of faster Mars transit is understood. What remains is the engineering maturation and the political will to fund it. Assume the crew survives transit. They arrive. They descend through the thin Martian atmosphere in an entry vehicle, a technically demanding maneuver because the atmosphere is simultaneously too thin to use parachutes alone and too thick to ignore entirely. The entry, descent and landing sequence, EDL in mission planning shorthand, has been called 7 minutes of terror for robotic missions. For crewed missions carrying much heavier payloads, it is even more demanding. SpaceX's solution for Starship is propulsive landing, using the vehicle's own engines to slow descent in the final phase, exactly as Falcon 9 boosters land on Earth. This requires the Martian atmosphere to decelerate the spacecraft from orbital velocity to a few hundred meters per second, at which point engines ignite for the final powered descent. It is an audacious approach. It has been tested repeatedly in Earth's atmosphere. Whether it will work flawlessly on Mars in dust storms with the specific density and composition of the Martian atmosphere, That question will be answered definitively only when it is attempted. The crew walks out. What do they feel? Gravity hits them first. 38% of Earth's, after 9 months of none. Everything weighs something again, but less than they remember. Their bodies, adapted to weightlessness, must now rapidly readjust. Muscles that have atrophied over months are suddenly required to lift the weight of pressurized suits. Suits that on Mars weigh approximately the same as on Earth, since gravity still acts on the suit's mass. The horizon is closer than on Earth. Mars is a smaller planet. You can see the curvature more readily. The sky, this is the thing that photographs never quite capture, is not black, not blue. It is a brownish pink, the colour of a sunset that never quite resolves. Fine dust particles suspended in the thin atmosphere scatter sunlight differently than Earth's sky. Sunsets on Mars are blue, in a reversal of Earth's experience. The Sun, viewed from Mars, appears about 2/3 the size it does on Earth. Still bright enough to be dangerous but diminished, distant, a reminder that you're no longer in the inner solar system. The silence outside the suit is absolute, or rather, it would be if you could hear it. The thin atmosphere transmits sound so poorly that the Martian wind, even in a substantial storm, would be nearly inaudible to an unprotected ear. Inside the suit, you hear your own breathing, your own heartbeat. The communication system crackles with the voices of your crewmates. Beyond that, nothing. Survival begins immediately. The habitat, pre-deployed, tested, running, is the crew's lifeline. Current NASA and industry habitat concepts for Mars surface operations fall into several categories. Rigid metallic modules, similar in concept to ISS segments, offer structural robustness but limited volume. Inflatable habitats, like the Bigelow Aerospace Beam module tested on the ISS, offer dramatically more volume per kilogram of launch mass, and are designed to withstand radiation and micrometeorite impacts. Hybrid designs combine a rigid structural core with inflatable volume extensions. The habitat must maintain sea level atmospheric pressure, approximately 101 kilopascals, or at minimum a reduced pressure oxygen-enriched atmosphere down to perhaps 55 kilopascals, a compromise that saves structural mass while maintaining adequate oxygen partial pressure. Every seal, every airlock, every pressure port is a potential failure point. Leak detection systems run continuously. Redundancy is built into every life support subsystem, not just single backup, but often triple redundancy. The philosophy that Mars cannot be a place where a single point of failure kills everyone. Water recovery systems on Mars will mirror and exceed those of the ISS. The current ISS environmental control and life support system recovers approximately 93% of water from humidity, urine and other sources. Mars missions will target 98% or higher, because every kilogram of water not recovered must be replaced from the ice mining operation, which consumes energy and time. Closed-loop life support is not just an engineering goal, it is a survival requirement. The medical situation is particularly sobering. A Mars crew must be capable of performing complex medical procedures without immediate contact with Earth-based specialists. Communication delays of up to 44 minutes round trip mean that in a surgical emergency, the crew is on its own. Mission crew selection will include individuals with medical training, likely at least one physician and one trained paramedic or surgical assistant. The habitat will carry comprehensive medical supplies including surgical instruments, ultrasound equipment, medications for the full range of anticipated conditions, and detailed procedural guides. But what about conditions not anticipated? This is where Dr. Darva Newman, former NASA Deputy Administrator and MIT Professor of Astronautics, has argued most forcefully for a new approach to space medicine, one built on real-time biosensing, predictive diagnostics, and AI-assisted medical support. Her biosuit concept goes beyond radiation protection to envision a suit integrated with health monitoring sensors that continuously track the wearer's physiological status. Combine that with machine learning systems trained on extensive medical databases, and you have something approaching an autonomous medical advisor capable of identifying deteriorating conditions and suggesting interventions before a crisis develops. The first Mars crews will spend enormous amounts of time doing geology, samples, core drilling, chemical analysis. The science return from a human geological survey of Mars will be incomprehensibly larger than anything achieved by robotic missions. Human geologists can cover territory, make intuitive connections, and perform in-field analysis in hours that might take a rover months. And the geology matters beyond pure science, because understanding the Martian subsurface is directly relevant to finding water ice deposits, to identifying stable locations for underground habitats, and to assessing the long-term geological stability of proposed settlement sites. Some might wonder, why not simply send better robots? Why risk human lives when robotic systems are becoming so capable? The answer is not purely sentimental, though sentiment is part of it. The answer is functional. Robotic systems require explicit programming. They can only do what their code anticipates. Humans adapt in real time to completely novel situations. When Opportunity rover's drill became stuck on Mars in 2015, it took months of Earth-based engineering effort to diagnose and address the problem. A human geologist on site would have assessed and responded within hours, if not minutes. The cognitive flexibility of a human being in a complex environment has not yet been replicated by any robotic system, despite extraordinary advances. And there is another answer, a deeper one. Humanity is a multiplanetary species only if we actually leave. The knowledge that human beings have physically stood on another world, breathed recycled air under an alien sky, planted food in alien soil, that knowledge changes something fundamental in the human story. It expands the boundary of what is possible. It shifts the existential risk equation for our species. Because a civilization confined to a single planet is a civilization one catastrophic event away from extinction. An asteroid, a pandemic, a nuclear exchange, a climate collapse. Whatever the mechanism, the fragility is real, and Mars is not just a destination. It is, in the deepest sense, an insurance policy for everything we have built and everything we might yet become. That is the peak emotional moment at the heart of this story, not the engineering solutions, not the ISRU calculations, not the radiation shielding formulas. The real reason to survive Mars is to ensure that the human story, this astonishing, improbable 4 billion year evolutionary narrative that culminated in creatures who can look up at the night sky and ask questions about what they see, continues. Every obstacle we have discussed, the radiation, the cold, the thin air, the toxic dust, the psychological isolation, the long dark of the transit, every single one of them is solvable. And the solutions are not theoretical abstractions. They are being worked on right now. By real people, in real labs, funded by real dollars, racing against a launch window that in geological terms is already almost upon us. The question isn't whether Mars will try to kill us. It will. The question is whether we will be good enough, smart enough, determined enough to refuse. History suggests we are, but this raises an even bigger question. Surviving Mars in the short term, a 3-year mission, a small crew, a carefully prepared base, is one challenge. Surviving Mars in the long term, permanent settlement, generational population, a self-sustaining civilization, is a profoundly different one. And the gap between those two goals is not just technical. It is biological, it is social, it is philosophical. Let's begin with the most fundamental biological question. Can human beings reproduce successfully on Mars? The honest answer is that we do not know. This is one of the most significant gaps in our knowledge. And it is a gap that is difficult to fill without actually attempting reproduction in a low-gravity, high-radiation environment, an experiment that would require careful ethical consideration before any human would knowingly participate. What we know from animal studies is cautionary. Reproduction in space has been studied in simpler organisms, fruit flies, nematodes, sea urchins, with mixed results. Some organisms reproduce successfully in microgravity, others show altered development, abnormal growth patterns, increased mutation rates. Rat studies conducted on shuttle missions in the 1990s found that pregnant rats in space showed disrupted uterine development in their fetuses. The rats did not give birth in space. The missions weren't long enough, but the developmental disruptions observed were significant. Mars's 38% gravity is not microgravity. It may be sufficient to support many aspects of normal reproduction and fetal development, but may be is not certainty, and certainty is what you want when the stakes are human lives. The cardiovascular system that develops in a Mars-born child would be adapted to 38% gravity. Their bones, their musculature, their vestibular system, all calibrated for Mars. Return them to Earth, and they would find Earth's gravity crushing. They would be Martians in a literal physiological sense, not just a nominal one. This isn't necessarily a problem. It might in fact be the beginning of a divergence that spans centuries, a gradual adaptation of the human form to Martian conditions. Natural selection, given enough generations and enough reproductive isolation. It is patient and thorough. A Mars population isolated from Earth for 500 years might look and function subtly differently from their terrestrial cousins. Give it 5,000 years. This is the beginning of a genuinely extraordinary possibility, one that has occupied philosophers, biologists, and science fiction writers for generations. But that is now entering the domain of serious scientific consideration, the possibility of a new branch of humanity. But before evolution, there is survival. And one of the most ambitious survival proposals for long-term Mars habitation doesn't involve adapting humans to Mars. It involves adapting Mars to humans, terraforming. The concept is straightforward in outline and staggering in scope. Modify the Martian environment, its atmosphere, temperature, and surface chemistry, until it resembles Earth closely enough to support unprotected human habitation. No suits, no domes, open sky, breathable air. The first step in most serious terraforming proposals is warming the planet. Mars is cold partly because its atmosphere is so thin. It can't retain heat effectively. Warm the planet and water ice begins to melt. Melt ice and water vapor enters the atmosphere, a greenhouse gas that causes more warming, which melts more ice, in a self-reinforcing cycle. This feedback loop, once triggered, could in principle run for centuries without additional intervention. How do you trigger the initial warming? Multiple proposals exist. Carl Sagan, in the 1970s, proposed darkening the Martian polar ice caps with dark dust to reduce their reflectivity and absorb more solar energy. A more ambitious proposal involves deploying enormous orbiting mirrors, structures perhaps hundreds of kilometers in diameter, positioned to focus sunlight on the Martian poles. Atmospheric science pioneer Dr. Christopher McKay, now at NASA Ames Research Center, has proposed introducing powerful greenhouse gases, specifically designed fluorine compounds, into the Martian atmosphere. These synthetic gases, produced from Martian surface materials, could be enormously more potent than CO2 as heat trappers. Theoretical models suggest that aggressive greenhouse warming could raise Martian surface temperatures enough to melt the polar ice caps and trigger significant atmospheric thickening within centuries, within 1,000 years under optimistic scenarios. Mars might have a thick enough atmosphere to allow liquid water on the surface and to provide meaningful radiation shielding. Plants, specifically engineered radiation-resistant variants, might be able to grow in the open Martian soil, beginning the long process of oxygenating the atmosphere through photosynthesis. Full terraforming, an atmosphere breathable without equipment, is a project measured in geological time. 10,000 years, 100,000 years. The timescales of civilizations, not of engineering projects. But even partial terraforming, thickening the atmosphere enough to allow simpler suits, raising temperatures enough to maintain liquid water in sheltered locations, reducing radiation to tolerable levels, could transform the economics of Mars colonization within the span of a few hundred years. Is this ethically permissible? This is a question that serious researchers debate with genuine intensity. If Mars harbors life, even microbial life, even dormant life, even remnant traces of ancient life, then terraforming that world destroys or permanently disrupts whatever biological narrative Mars has been writing for 4 billion years. The discovery of even a single living cell on Mars would be, in the words of planetary biologist Sarah Walker of Arizona State University, the most important scientific discovery in human history. Evidence that life arose independently, twice, in the same solar system, would mean life is not an accident. Life is an inevitability. Life fills the universe, and we would be proposing to bury that life under a new atmosphere we designed for our convenience. The counter-argument is also powerful. If Mars is biologically dead, if, as most current evidence suggests, any life that once existed there was extinguished billions of years ago when the atmosphere collapsed, then a lifeless desert world is not served by remaining a lifeless desert world. What moral obligation do we owe to preserved emptiness? Planetary protection protocols currently require that any Mars mission avoid contaminating the planet with Earth biology, precisely so that future life detection missions have a clean baseline to work with. Perseverance's sample cache, scheduled to be returned to Earth by a joint NASA-ESA campaign in the early 2030s, will be the most significant test of the contamination question yet. If those samples come back containing ancient biosignatures, the terraforming debate will immediately become the most important ethical and political conversation humanity has ever conducted. Back to the more immediate question of survival. Long-term Mars colonies face social and political challenges that no engineering solution addresses. A community of even a few hundred people, isolated from Earth and dependent on collective cooperation for survival, operates under different rules than any society humans have previously organized. Every member's survival depends on every other member's competent and willing contribution. In that context, social conflict isn't just uncomfortable, it's lethal. The history of isolated human communities, Antarctic stations, early submarine crews, closed ecological research stations, provides some guidance. Strong shared purpose, clear role definition, effective conflict resolution mechanisms and careful crew selection for psychological compatibility all appear crucial. The most successful isolated communities share a common characteristic. The individuals within them genuinely believe the work they're doing matters. On Mars, that belief will not require cultivation. It will be self-evident every moment of every day. The governance question is also non-trivial. Who makes decisions for a Mars colony? If the colony is funded by NASA, does the United States government have jurisdiction? The Outer Space Treaty of 1967, the foundational document of international space law, specifies that no nation can claim sovereignty over a celestial body. But it says nothing coherent about private citizens, corporate entities, or self-governing communities on those bodies. As Mars colonization approaches reality, the legal vacuum left by 50-year-old treaties becomes an increasingly urgent problem. SpaceX's terms of service for Starship, updated in 2021 to explicitly reference Mars, contained language acknowledging that current Earth-based laws may not apply to a Martian settlement, and that a new framework of governance may be needed. This is both legally interesting and potentially alarming, depending on your perspective on who gets to write that framework. A Mars colony that becomes self-sustaining will, by definition, reach a point where it no longer needs Earth's support. At that moment, the moment of economic independence, the political relationship between Mars and Earth becomes genuinely undefined. Are Martian citizens of Earth nations? Are they a new nation? Are they beholden to the laws and frameworks of a world they may never have visited, and whose gravity they can barely tolerate? These questions sound philosophical right now. Within a century, they could be the defining political questions of human civilization. And underneath all of it, underneath the engineering, the biology, the politics, the ethics, there is a simpler, older question. One that humans have been asking since the first band of our ancestors walked out of East Africa into unknown territory. What is waiting for us out there? Mars may answer that question in ways we cannot yet imagine. The rocks of Mars, ancient, largely undisturbed, covering the full span of the solar system's early history, contain a geological record that Earth has mostly lost to tectonic activity and erosion. The Martian crust holds archives of the first billion years of solar system formation. Human geologists walking those ancient highlands, examining rocks that haven't been touched by any process since the Noachian period, 3 to 4 billion years ago, will read a story that reshapes our understanding of how worlds are built. And if, buried somewhere in that ancient rock, or frozen in some deep aquifer, or preserved in some peculiarly sheltered geological feature, life is found, even dead life, even molecular traces of what once was alive, everything changes. The context of our own existence shifts. The probability of life elsewhere in the universe upgrades from hopeful guess to near certainty. The Fermi paradox, that great silence from the cosmos, that absence of alien signals that has haunted physics for decades, acquires new urgency. If life arose on Mars independently, why isn't the universe teeming with it? Where is everyone? Mars is not just a survival challenge, it is a question. We began this journey with a simple, brutal statement. Mars is trying to kill you, and it is. Everything we have examined, the radiation, the cold, The airlessness, the isolation, the dust, the physiological degradation, the psychological pressure, the distance from help. Every single element of Mars conspires against the human organism. Mars did not evolve to receive us. It has no interest in our survival. It will not make concessions, and so we must make them ourselves. What we have discovered across this journey is something that should be both humbling and deeply exciting. The gap between Mars as a death trap and Mars as a human home is not a gap of impossibility. It is a gap of engineering, of medicine, of psychology, of political will, of time. Humans have crossed wider gaps than this. We have survived ice ages with stone tools. We have sailed across featureless oceans using nothing but stars. We have stood at the bottom of the sea and the top of the stratosphere and found, each time, that the human body and the human mind, pushed to their absolute limits, do not simply break, they adapt. The first people to land on Mars will face extraordinary danger. Some may not survive the journey, some may not survive the landing. The early years will demand everything from the people who attempt them. History will record their names. We will tell their stories to our children the way we now tell the stories of Magellan and Shackleton and Armstrong, as proof of what this strange, restless, impossible species is capable of when it decides that something must be done. And then, generation by generation, mission by mission, Mars will become less hostile, the habitats will expand, the life support systems will mature, the medical knowledge will deepen, the ice mines will feed the water recyclers, the perchlorates will be leached from the soil, green things will grow under red LED lights in pressurized tunnels beneath an alien sky. And eventually, perhaps in 100 years, perhaps in 200, a child will be born on Mars who has never known Earth's sky, who has never felt the pull of a full gravity, who looks up at the bluish sunset and feels at home. That child will be the answer to our question. Can we survive Mars? Yes. Not easily. Not without cost. Not without loss. But yes, with the same fierce, irreducible stubbornness that has carried our species across every hostile threshold we have ever encountered. There is one thread we have left unresolved, one question that sits beneath all the others, waiting. It is this: if we can survive Mars, what does that mean for the rest of the solar system? Europa, with its vast subsurface ocean, Titan, with its lakes of liquid methane and its thick sheltering atmosphere, the asteroids, the Kuiper Belt, the long dark between stars. Mars is not the end of the story. Mars is the first sentence of a story so long and so strange that even our most expansive imagination can only guess at its next chapter. And somewhere out in the dark, that chapter is already waiting to be written.